Greetings. One of the proofs from antiquity that we need to discuss in this course, obviously, is the theorem on right triangles. You probably know it as the Pythagorean theorem. The theorem simply states that the square on the hypotenuse is equal to the sum of the squares on the legs. And we have a diagram of this to our side. And what the idea is to say is that if somehow I add this square to this square, it must be equal to this square right here. Because using the word square is how the Greeks talked about a number, an area having a number associated with it. In our terms, we look at it in modern language, we worry simply about the numbers. But for the Greeks, it was much more. It was, how do I show that I can transform a square onto another square, or part of it? So with that being the case, I want to present Euclid's proof of the Pythagorean theorem. And Euclid began with a classic style right triangle with squares on the legs and the hypotenuse. And Euclid began by pointing out the first piece. Euclid took a line segment from the right triangle's right angle vertex, and it had to be perpendicular to the hypotenuse, and likewise it's perpendicular to the opposite side of this square. It is also, and more importantly, parallel to these two sides of this square. And we're going to talk about why that's important in a moment. So Euclid began with this very idea. And then Euclid said, now let us look at a couple of facets of what's going on. One, let's take a look at another line segment. And again, from the right angle, he is going to come across, and he comes up here to one of the corners of the hypotenuse, or I'm sorry, of the square on the hypotenuse. Likewise, he is now going to take and he's going to show us a second segment that is going to come this time not from the right angle of the right triangle, but it's going to come from this upper side of the right triangle, coming across, in this case, the larger of my two legs. And Pythagoras is going to try to, not Pythagoras, but Euclid is going to try to make an argument about something that's going on here. And so let me show you what he's going to talk about. He's going to talk about triangles, and namely that triangle and this triangle. Now, before I get carried away with these two triangles, I need to show you something very peculiar about a triangle. So I'm going to hide this one down here. I'm going to look at just this one for a moment. And I'm going to come up here and I'm going to measure its area. All right, so I have a measurement right here, and you're going to have to permit me. I'm going to have to change its color to yellow so that we can continue to see it. And I can move that vertex, and I get different triangles. But notice the area is not changing. And the question is why? And this is what Euclid's going to make use of. Euclid noted that between two lines that are parallel to each other, if I were to take and draw a triangle, and we name this side the base, we know that the area of this triangle is 1/2 the base times the height. Well, the question is, what is the height? And if it's parallel lines that we have, we know the height is typically thought of as being the distance from the third vertex in a perpendicular fashion to the opposite side. But what happens if I move this point right here over to now be right here? So I now have a new triangle. Here's my vertex. So I come from the base, because I did not move the base. But I now have this red triangle. But it has to have an area that is 1/2 base times height. The base did not change because I've left, let's say, points A and B fixed. What I've done is gone from a C1 location to a C2 location. But if these two lines are parallel to each other, what did we know about the height? Well, I could remeasure, but I know the measure between parallel lines is a constant. That means that a triangle trapped between parallel lines must have the same area as long as we leave the base fixed. And that's what we see right over here. When I drag this point back, I see this formula telling me my area is not changing. And it's not changing because this line we said was constructed so it would be parallel to this side right here. That being the case, it's going to allow me to do something interesting. Let's get this back down. Let me move this point. And I'm going to show the other triangle. Now, in order for me to continue my discussion, let me get rid of this stuff I don't need to see anymore. And I'm back. Now let's look at this diagram over here, and I'm going to name some of these points so that we know exactly what we're talking about. At the right angle, I'm going to refer to that point as the point C. Over here at this side of the triangle, I'm going to refer to this as point A. Up here, I'm going to refer to this as point B. So I have a right triangle ABC with right angle at C. So the proof of Pythagoras' theorem, using Euclid's methodology, step 1, construct the segment from C, and I'll name this point up here H. Now then, what we want to do is talk about what this means. So first off, in step 1, we're going to construct C to H parallel to, and I need to name another point, so I'm going to name this one right here, and I will name it I. So AI, and I constructed parallel, and I know that I've constructed squares on the sides, would be the first thing I would point out. So I've got this construction, so now I can talk about these triangles in a certain way. Now let's talk about these two triangles. And I'm going to first off talk about, and so I'll hide one of them, so I'll only talk about one at a time. Let's look at this first triangle. Triangle, and let's name it starting at C. C-A-I. Now, C-A-I, I know has 3 segments to it. So I have segment C to A, and I have segment A to I. And those are the two that I want to focus on right now. Now then, I want to look at the second triangle that I can put up here. So I'm going to hide my first one, and let's show you the second one. This triangle now, I need to name a point down here. So I will name this one point G. And so triangle, and I'm going to start with BAG. I know it has sides B to A and side A to G. Now then, you ask, well, what's so special about those sides? So I want to talk about where these triangles have pieces related to the various squares. Look at the large square, the square on the hypotenuse. I see one of the triangles, the green one, has a side on that square, namely B to A. So B to A is on the square dealing with the hypotenuse. The yellow triangle, this one right here, has a side on the square on the hypotenuse, namely a to I. So in other words, since I know that this figure right here is a square, I know that BA must be the same in length as AI. And that's useful to me. Now, let's look now at the smaller square, the square on the longer leg down here. The question is, do these two triangles have a side that's related to this square here? And the answer is yes. If we look at it, we can see that the yellow triangle has sides C to A. So C to A is a side on a leg. And then namely, if we take the green triangle, this one right here, it's on A to G. So the legs, or some of the sides of those triangles, match up with each other. But also something else is fascinating with both of these triangles. Look at angle CAI. Angle CAI is I'm going to call it a composite angle. It's made of two pieces. This little angle right here at A, and I call it A because it's CAB, it's the angle inside my original right triangle, and a right angle. Now look at the green triangle for a moment. It has angle BAG. Now let's talk about angle BAG for a moment. BAG is an angle, and it's also a composite made up of two smaller angles. Again, it's the angle in the right triangle at vertex A and a right angle. So it wouldn't take much for us to argue that these two angles must be the same size. And if we look at these sides right here, I can now conclude by side angle side that triangle CAI is congruent to triangle, and let me get my naming straight. If we're going C to A to I, little, so it's this leg, then out onto the hypotenuse. So for the green triangle, it needs to be GAB. But those triangles are congruent. And if they're congruent, you know what else we know? They have the same areas. So that means these two triangles have exactly the same area. And we're hunky-dory. We're happy with that. Let me show you why. I'm now going to move this vertex to right here. And I'm going to take my other triangle and I'm going to move its vertex to right there. Now remember, we saw that triangles between parallels must be equal to one another in area. So this yellow triangle that we see right now has the same area as it had before we moved it. Just as the green triangle must have the same area as the triangle we had before we moved it. Therefore, these two triangles now still have the same area, but let's notice, I now have CAG. And CAG is exactly 1/2 of this square right here on the long leg. Likewise, we now know that this kind of golden colored triangle is exactly 1/2 of this rectangle that we see that makes up part of the square on the hypotenuse. So this square on the long leg is equal to this rectangle piece inside of this square. So far so good. Let's hide what we don't need now. Euclid wasn't finished. Euclid said, now, let's get on and do the same thing again. Because what Euclid now realized was if I could show that this square mapped onto this little rectangle, tickety-boo. I'd be able to say this square to this rectangle, this square to this rectangle, these two squares combined to this square. And that is the statement of the Pythagorean theorem. So let's take a look at two triangles. And I'll have to move them to their proper position to start the proof. But let's take a look at where they are. So now I'm looking at two different triangles. So now we're in basically what I would call step 3, where this step 1 was construct this perpendicular, make the argument about the squares on the sides. Step 2 was to show me that I have congruent sides, congruent triangles, and then make the argument about equal areas between parallels. And now on to the third part of the proof is to say, let's pick up two new triangles and see what happens. So let me name this point out here, and I'll put this out here at F. So now we're going to talk about triangle FB to A, and we'll talk about triangle CB, and I'll need to name another point. And since I'm up here, I'm going to call it J. You can name the points anything you want. They're simply labeling variables, dummy variables. Now, let's take a look. Just as we did previously, I now want to look at the pieces of these triangles. So, I know I have a segment FB, and I have a segment from B to A. For this triangle down here, I'm going to have a segment from C to B, and I have a segment from B down to J. And we're going to likewise get some bits of information about angles in just a moment. But let's take a look at our triangles first. Well, F to B is a piece along the the small square. The square built on the shorter of the two legs. So F to B must be the same as B to C. So F to B is on my smaller square, just as C to B. So these two sides right here that I just underlined must have the same length. Now, I can then say, let's look at B to A. And B to A is a side along the square on the hypotenuse. Well, B to J is also along the square on the hypotenuse, so BA must be the same as BJ in length. So I have two sides of this triangles matching up to one another. Now let's look at this common angle right in here. And we notice we have the angle from A to B down to C is common to both the green and the pink triangle. And notice both triangles include a right angle. So they're composite angles. With a little bit of discussion, I can very easily make the argument that angle FBA must be the same in size as angle CBJ. Now then, with that being the case, I can once again argue by side angle side that I'm going to have two triangles congruent. Namely, I have triangle FBA is going to be congruent to triangle CBJ. Well, if they're congruent, we know that their areas are the same. And if their areas are the same, that's really nice. Now, notice I can grab the vertex at C for the green triangle, and I know all of these green triangles have the same area captured between parallels. I'm going to park this point right here on this side of the square on the hypotenuse. Now I'm going to take the vertex at A and I'm going to move it off using the pink triangle and bring it over here to C. And now we're going to talk about what we can see. We know this pink triangle must still have the same area as the green triangle. But the pink triangle is exactly 1/2 of the square on a leg. And the green triangle is exactly 1/2 the area of this rectangle that's part of the square on the hypotenuse. Now this is where it gets really fascinating. So I've just demonstrated that half of this square matches up with half of that rectangle. So it makes sense that this square matches that rectangle. We know that this square matches that rectangle. So when I add all of this together, I have demonstrated that the sum of the squares on the legs is equal to the square on the hypotenuse. And that is the technically correct way to state Pythagoras' theorem. By the way, he wasn't the first person to come up with it, but his name did get associated with it. I hope this helps.